A 4.6 kilogram ball with a radius of 0.5 meters is fired at an initial speed of 27.2 meters per second and at an angle of 47.3 degrees. It is traveling through a fluid with a viscosity of 0.32. This is our simulation of a projectile fired without air drag. Here we're entering its radius at 0.5 meters. Its mass is at 4.2 kilograms. The drag coefficient, which is the viscosity of the fluid, is 3.2. Our initial speed is 27.2 meters per second, and our angle is 47.3 degrees above the horizontal. It traveled a total of 75.44 meters, and so this is our simulated projectile with no air drag. Over on the left-hand side, you'll see our free body diagram, and the only force acting upon it is its weight. On the right-hand side, you'll see the graph of its flight. It is fairly uniform and symmetrical due to the uniform due to the constant forces on it. There's no changing forces on it, so the graph is very uniform. Okay, so this is the code for our defining our variables on our Python program. So line 3 sets the radius of our projectile. Line 4 sets the mass of our projectile. Line 5 defines the viscosity of the fluid we are firing our projectile through. Line 6 defines the initial velocity that we are firing our projectile at. Line 7 gives us our initial angle that we are firing it at. Line 8 converts that initial angle in degrees into radians. Our line 9 gives us our velocity vector, and it is splitting the initial velocity into its x and y components. Moving on to line 10, this is the initial location or position of our ball. It's moved up the radius of the ball in order to make it rest on the ground. And then line 11 defines our gravity in vector form, and it's just negative 9.8 meters per second in the y direction. Alrighty, so this is the actual physics behind our simulation. That's where all our variables come in and actually make the ball move. Starting off on line 19, this is how fast our program runs basically. Going on to line 20, this causes our program or our simulation to end when y becomes less than r. So basically when the ball hits the ground is when the simulation will end and stop collecting data. 21 is the rate in which it carries out its calculations. So the lower the amount of calculations, the more jumpy the ball's movement is, the higher, the more smoothly the ball moves. 22 is the acceleration in our problem. In this problem, we have no air resistance, so the only acceleration is due to gravity, right here. Next is our delta position, which is given by our velocity with respect to time. So change in position equals velocity with respect to time. Now next is our change in velocity, and this is given by acceleration with respect to time. Next is our position, and our position is given by position plus the change in position, so the initial position plus the change in position. Next comes the velocity. So the velocity of our object is given by the initial velocity plus the change in velocity. Alrighty. Last but not least, this line 27, is actually what causes the motion in our simulation. So this causes the ball to move. So this is the position of our actual projectile, and that is given by the position of by this line right here. And this line is tied into all these other lines. So that's what gives our ball its movement in our simulation. Finally, line 29. This simply captures the range of the simulation and displays it at the bottom. So, alrighty. So, drag force and Stokes' law. Stokes' law is force or mass times acceleration equals 6 pi times the radius of the sphere times the viscosity of the fluid times the velocity of the object or the sphere. So we were given 5 variables. There's 4 of them in this equation: radius, viscosity, velocity, and mass. The angle the object was launched at doesn't matter to calculate the drag force because the direction of movement doesn't matter. So this law can only be used on round objects traveling through a fluid that does not have turbulent flow. The friction is a force that always acts in the opposite direction of movement. And in a projectile motion problem, the projectile is constantly changing direction as it undergoes acceleration due to gravity and friction. This makes these problems very difficult to solve by hand, and basically it's a necessity to solve them with a simulation. Defining variables in our code for projectile motion with drag. It's very similar to the code we used earlier for projectile motion without drag. In fact, it's the exact same. It's just later on in the code we will be using this defined variable b for the drag coefficient in order to calculate the drag force due to Stokes' law. So defining all the objects in our simulation with drag, again very similar to that of the simulation without drag. A few minor differences. Our camera is centered differently because the projectile travels significantly less far. And then we just changed the color of our projectile and our ground. This is our simulation of a projectile fired with air drag. I'm going to quickly run this program. So the radius of our projectile is 0.5 meters. The mass of our projectile is 4.2 kilograms. The drag coefficient, which is the viscosity of our fluid, is 3.2. Our initial speed is 27.2 meters per second, and our angle is 47.3 degrees above the horizontal. So the range of our object, the horizontal range that it went, is 22.85 meters. Simulated projectile with air drag. On the left hand side we have our free body diagram. As you can see, our ball or our projectile has 2 forces acting on it. The first one acting downwards is the force of is its weight, which is its mass times its gravity. The second of which is the frictional force caused by Stokes' law, which is 6 pi r times the viscosity times its velocity. And the frictional force always acts in the opposite direction of motion. And because its direction of motion is constantly changing, the frictional force is also constantly changing direction. Due to this constantly changing direction of the frictional force, it makes the graph not very uniform. It distorts the graph as the forces on it are not uniform and changing due to friction. So as we can see, it loses most of its velocity, x velocity, and so it appears to not travel very far on this second portion of its flight where it's falling. This is our comparison between the projectiles with and without drag. So you see on the right hand side we have two separate graphs. The top one is our simulation with drag, and the bottom one is our simulation without drag. The first major difference you'll see between the two is their shape. So our top one is not very uniform or symmetrical, while our bottom one is very symmetrical and very uniform. The reason for the difference in shape is because of the forces on the two. So let's start out with the bottom one, our simulation with no drag. So it's very uniform because the forces in it are, well, the force of gravity in it is very uniform. So the force is always acting down, force times mass, or not force times mass, mass times acceleration, so it's mass times acceleration. So its acceleration downwards is always the same, and this is what gives it a very nice shape, and it's only experiencing that acceleration downward. The second one has two different forces acting on it. It has gravity, which is very uniform force, always acting down. So it would have a nice shape if it weren't for the other force acting on it, which is the frictional force as it moves through the air. This frictional force we got from Stokes' law, and it always acts in the opposite direction of movement. This means it not only fights against the y component of movement, it also fights against the x component of movement. So we can see that that it slows down quite a bit quicker than our no drag simulation. So we can see it's just as steep as it is right here, but it dies off a lot quicker in both the its vertical velocity and horizontal velocity. We can see towards the end it has almost no horizontal velocity, and but its vertical velocity does pick up a bit again towards the end. This is because gravity is much stronger than the frictional force, or its the force of gravity is much stronger than the frictional force, so of course it's still going to fall to the ground. Because the forces on it aren't uniform and always acting in the same direction on this top one, it makes the graph not very uniform and symmetrical. The second big distinction between the two is the range. So on this first one, it only travels 22.85 meters. Well, on the second one without air drag, it travels more than 3 times as far at 75.44 meters. Again, this is because it spends more time in the air, as it only has to fight gravity in the y direction, and its horizontal velocity stays constant. Well, up here, it does not stay in the air as long because it must fight Stokes' law, or it must fight the frictional force in the y direction, so it doesn't stay in the air as long. And while it's in the air, it doesn't travel as far because its horizontal component, its x component, must also fight against the frictional force. So it's decelerating horizontally as it's moving through there as well, which it's not doing in this bottom one.